Hey math people. Today, approximating area under curve. So almost integration, but not quite integration. It's that pre-integration. Yeah, so these are the two formulas you need to know for today, but how do these connect to area underneath curvy things, right? So if I have some sort of graph and it has some twists and turns to it, how can we connect middle school geometry to something a little bit more abstract? Because if we're talking about this area underneath this curve, well, we're not talking about something as simple. Maybe I'm finding it from this point to this point. So maybe I call this A, maybe I call this B. And this area is not easy. Sure, it looks rectangular at first towards the bottom, but then all of a sudden it has its turns up top, and that's not something you can immediately apply these ideas to unless you use it as an approximation. So redrawing the same line, we'll do it over here. So this is kind of the right way of thinking about it. Maybe we have a very similar curve, and it's in a very similar window, still from roughly A to B. Let's just say I take on what's eventually going to be RRAM, like a right rectangular approximation method, or perhaps an MRAM, because you can draw these rectangles where the top of it meets the middle, and I'll draw this in a sec, of this curve. Lastly, there's another approximation method called LRAM. When you draw the rectangles, the top left corner of each rectangle is on this curve. How about I do LRAM? LRAM is a pretty common one to ask for. So I want to draw these rectangles, and maybe I want to draw 4 rectangles. Yeah, 4 rectangles. Such that the left endpoint is always on the curve. So you'll note right off the bat, I don't know if the camera will pick up on it, but there's a small sliver right there that I don't actually quite find the area of. You'll note on this next rectangle, it's actually a bit of an over approximation. I'm counting too much area. How am I going to draw this next one? Same story with the third and the fourth. So here we would call this an overestimation because these combined areas probably are over the actual area from A to B underneath this black curve. So this is LRAM. This is great. How about with the trapezoid approach? So we're just going to say, not yet. Because if you're watching this, I'm assuming you're either just reviewing so you know that there's real integration, you can actually find the area underneath the curves, or you're watching this and you've only done approximating area underneath the curves, and in which case, not yet to this. We're still in the approximation phase. So one last time, drawing the same idea, the same curve from A to B. This now being the trapezoidal approach. Here's the thing, trapezoids can be orientated in different ways. You can perform a little rotation, you can say counterclockwise 90 degrees, and that might be a little helpful. Also, you don't have to have these shapes. You can draw a trapezoid like this. There we go. You can have some perpendicularity within the trapezoid. The only thing you really need in the trapezoid is that these opposite sides need to be parallel. So what I can do is I can just perform a little rotation on this. And all of a sudden, we can start getting a little bit closer in our approximation to the actual area underneath this curve. So maybe I ask the same thing. Maybe I ask the same number of subintervals. And now when I draw the area or these shapes, it's starting to match the shape a little bit more. So you'll notice that this largely looks like it's going to be, this will be a very close approximation, because here I think I'm going a little over. These two will be probably slight over estimations, and these two are slight underestimations. This is a line here. This is not a perfectly horizontal line. So I do still miss a little sliver. I'm not sure if the camera picks up on it, but it's less significant than saying this overestimation, which is quite large relative to this small sliver. So just point being is we now can kind of create a linear path here that isn't perfectly horizontal that allows us to get a slightly closer approximation. So this is using a trapezoid approach. This is LRAM. You can do the same thing with MRAM, so you can meet the midpoints of each rectangle onto the curve, or you can do the same thing with RRAM, meeting the right endpoints to the curve. So you'll get slightly different approximations for these three. And typically trapezoid is your best bet. That's usually going to be the closest of these four. There's other approximation methods, but these are the four we're going to talk about today. Anyway, let's start actually doing the math. Okay, looking at our first one, we have something really basic, a line. Y is equal to x plus 6 from -2 to 2. Helps to draw it. So let's do that maybe over here. So should have drawn maybe a bit farther to the left there. Okay, -2, we'll call it over here, and +2, we'll say it's over here. X plus 6, okay, so 1, 2, 3, 4, 5, 6, so we're all the way up here. Looks generally like that. So we're looking for the area from -2 to +2. And we're going to use left endpoints, similar to the case I just drew earlier. So, looking at the number of intervals, the number of rectangles desired, it wants 4 of them. So we need to split, the first step is to split the interval into the desired x length of each and every rectangle. The way we do that is pretty simple. We just take, b minus a over n. And what this is going to be my change in x. These are going to be the lengths of, or we can say the widths of each rectangle. So if the length represents the height, then the width is that left to right movement of each rectangle. This is the formula we use to find that, where this is my a and this is my b. Okay, let's use it. So my b is a 2, my a is a -2, and n is the desired number of rectangles, in which case it's 4 here. So we're going to say 4. Anyway, math comes out really nice and pretty for this one. You get 2 plus 2 up top, that's over 4, so 1. The length of each rectangle is 1, and that should make sense, because we're going to have rectangle here, we're going to have rectangle here, we're going to have rectangle, wait. Don't like that I accidentally erased that. We're going to have one rectangle here, one rectangle here, one rectangle here, and then the fourth rectangle here. So that's how it's going to look. Actually, I can even draw it out. Why am I just talking about it? And hey, is this going to be an over or underestimation? Let's think about this. Are these, the areas of these rectangles, are they going to be more or less than the actual area underneath this line from -2 to 2? I don't know. We'll see. Maybe you should have an answer in your head. It should be pretty obvious. But let's prove it numerically. LRAM, 4 left endpoints. Let's do this. So let's find the area of each individual rectangle. Here, we notice that the delta x is 1, so the widths of each of these rectangles is just 1. That's not too bad. Let's find out these heights. So the way that these heights are appearing to work out, this height is going to be f of -2. This is just the output at -2. This height is going to be f of -1. This height is going to be f of 0. And then finally, this height is going to be f of 1. So those are the lengths. I obviously need to actually compute them, though, by plugging in stuff, but let's show our work for it. So we're going to say this. We're going to say the area is equal to. Need a little bit more. Right. Area is equal to. Or approximately equal to, because this is an approximation method after all. Okay, so the area of the first rectangle is its length times width, so it's going to be f. It'll be 1 times f of -2, plus, next one would be 1 times f of -1. Next one is going to be this length of 1 times f of 0. Last one's going to be this length of 1 multiplied by this length here, which is f of 1. Alright, so I have to actually find all these now. So I'll say that this sum is now equal to the following. F of negative 2, if I take a negative 2 and I plug it into this thing, what shoots out? What's the y value? That should be a 4. So it's going to be 1 times 4. Negative 1, if I take that and I plug it into here, I get a negative 5. So it'll be 1, or positive 5, so that'll be 1 times 5. 0, if I plug a 0 in, that's just 6. And lastly, if I plug in 1 here, f of 1, 1 plus 6 is 7, so I'm going to get 1 times 7. And it makes sense that these lengths are getting larger over time. We go from 4 to 5 to 6 to 7, because this has a height of 4, this has a height of 5, this has a height of 6, and this has a height of 7. Anyways, math here is not too bad. It's just 4 plus 5 plus 6 plus 7. That's 9 and 13 to make 22. So this is the approximation of the area using LRAM for left endpoints. How about if we use 8? Is that going to make my estimation closer to the actual area or further away? Let's find out, because we're going to actually find the area in a sec here. Alright, so same kind of logic. Let's find my delta x though. Here, I'm going to need a little bit more room. You see, I was running out of space here because I took the sum of 4 rectangles here. I'm now asking you to find the sum of 8 rectangles. Yikes! So I'm going to need a long string there. I'm going to say delta x in this case is equal to... okay, so top doesn't change. It's still the same numerator. It's still a b value of 2, and it's still an a value of negative 2. However, the denominator here, this n, now changes, provided that I want 8 rectangles instead of 4. So my delta x, my width of each independent rectangle actually just got a lot smaller. I have 4 over 8, which is a half. Okay, so that's weird. These areas are now all shrinking. However, I'm adding up more rectangles, so you'll see that that's going to make a substantial difference. So play around with the idea of, well, what if we draw 8? Man, I'm going to ruin some markers here. If we were to draw 8, a little harder to see, but you should see or note that these little triangles that were inside are starting to fill in a bit. We're creating more triangles inside, but they're really small. So we're getting closer and closer. That's the idea here. This is going to be a better approximation to the actual area because I am kind of smoothing out all these ridges. So consider if we had 1,000,000 rectangles inside, just how smooth that would be. It would be almost not noticeable to the human eye. It would just look like the actual area itself. It'd be like very tiny pixels. You wouldn't really be able to see that. Area in this case approximates to. So now the width of all these rectangles is a half. So instead of multiplying by this width of 1 each time, I'm going to be multiplying by a width of a half each time. I'll show a shortcutted approach to this. This is assuming equal length intervals. Sometimes the interval lengths do change though. So first rectangle, it's going to be half, and it's still LRAM, so it's still going to be the first output, which is f of negative 2. Okay, the next one. So I'm moving half an x value to the right. So I was once on negative 2, I'm now on negative 1.5. Move half over again, so instead of being at negative 1.5, I'm now on negative 1. One, two, three. So my fourth one, move a half to the right again, so it's going to be 1/2 times f of negative 0.5. So that's half of the work here, so I'm still writing another chain. I'm going to continue this. Still a half again, but this time around I'm on f of 0, and hopefully you're kind of picking up on a pattern here. I'm adding half every time to the input, so f of 0.5, half of f of half times f of 1, and then very lastly we have half of f of 1.5. And this should have, since we're asking for 8 left endpoints, you should have 8 terms here. 1, 2, 3, 4, 5, 6, 7, 8. Great. This is the same thing as, so this is equal to, the shortcutted approach to this, since these were equal length intervals, like these were all 1/2, you could have just factored a half out, and then you could have taken the sum of all of these independently. And this is a great shortcutted approach, but something I would be careful with, because if the intervals aren't the same length, then it's not going to work. So this would be the alternative way of writing this. You could technically factor out a half from this. You can just say, okay, I know the length of all these intervals is a half, or the width of all these intervals is a half, so I'm just going to keep that on the outside, and I'm going to, it's kind of like the factor of the sum of all of these lengths, right? Because you could have theoretically just factored out a half here, and that just saves you a little bit of time writing. You still have 8 terms. 1, 2, 3, 4, 5, 6, 7. What did I skip? Oh, I skipped a f of 0.5 here. Let's actually solve this out. So I'll say this is equal to, and I'm going to just keep the half on the outside here. F of -2 we already solved for. That was 4. F of -1.5, okay, that's going to be -4.5 or positive 4.5. F of -1 we already solved for. That was 5. And actually this pattern is just going to continue up until the 8th number. So 1, 2, 3, 4, 5, 6, 7, and then 8. Okay, some mental math. This should be closer. This should be 23. So what is the actual area? All right. One last time I'm going to draw this shape, because there was a better way of finding this area all along. This is just a line. So from -2 to 2, how could I have found the actual area, which looks like this? So this is a particular shape. This shape right here is actually a trapezoid. So one trapezoid would have gotten the job done. It's a trapezoid kind of laying on its side, where the parallel ends are these guys right here. So the height of this trapezoid is from -2 to 2. So I'm viewing the trapezoid this way. I'm like tilting my head and I'm viewing it as if it was rotated 90 degrees. The height of this trapezoid is this length right here, which happens to be a length of 4. So I'm writing it this way because I'm kind of observing it this way. As far as the b sub 1 and b sub 2 go, this is just going to be evaluated at f of -2, which we already did. So this is a length of 4 as well. Doesn't look like that, but my drawing's not perfect. And then over here, f of 2 we already evaluated at some point. No, we didn't, but it's just going to be 8. That's pretty easy. So I have my b sub 1, I have my b sub 2, and I have my height. So let's just plug it into the trapezoid formula, which we wrote earlier. So the actual area is equal to 1/2 b sub 1 plus b sub 2 times h. In this case, the half is rewritten. The b sub 1 is 4, the b sub 2 is 8, and the h here, the height, is also 4. So half of 4 is 2. 2 times 12 is 24. So the actual area is 24. When we used LRAM with only 4 rectangles, we ended up getting an area of 22, which was pretty close. We tacked on a few. We actually doubled the number of rectangles, and we got 1 unit closer. And the actual area, use just a trapezoid because it is just a trapezoid underneath it, it's 24. So with a trapezoid approximation, specifically for lines, that's going to be not an approximation, it's the actual, because it creates a literal trapezoid on the inside. This is not true for anything twisty and turny.
Okay, I'm on Desmos just to make this visualization a little bit more clear. Each of these little boxes actually represent an area of exactly 1. So you can actually count these, and this is the case where we had 4 left and endpoint rectangles, and you should recall that the answer was 22, and you can actually count that there are 22 boxes. And the actual area is 24 because we're missing out these on 4 half boxes. So 4 times a half is 2. So this area that is missing, these triangles, add up to an area of 2. We can actually amp this up to 8 rectangles. And all these little triangles on the inside are actually, I think they're fourths. Yeah, because quarter plus a quarter, that's a half. No, actually they're eighths. An eighth plus an eighth plus an eighth plus an eighth. Yeah, there's 8 of these, so you're missing out on an area of 1. All of these little triangles add up to an area of 1. And you can naturally amp this up to a really high number of rectangles. There's a point where if it gets too large, it's pretty much the same area. And that's technically if you take the limit of this toward infinity. And sure enough, you actually just end up straight up getting that trapezoid. Did too many zeros, couldn't register it. So in this case, this is just straight up the trapezoid. There's no missing area, and you get an area of exactly 24 this way.
Next on the agenda, we have some MRAM. We have a cooler looking curve, not a straight line. And we're going from -5 to -1 for rectangles. Let's do the same business with finding the length or width of each rectangle. So delta x, my change in the x values with 4 rectangles, should be a nice pretty number here. We have b minus a over n, so it'd be -1 minus -5 over 4, and hey, that's a nice pretty 1. So we ran into this, and 1a also occurring here on 2. Okay, let's be a little more abstract here. Let's try to visualize this in our heads. Let's try to not lean into the visualizations, and let's try to think about this just algebraically. Because if you're taking, say, an exam, an AP exam, or a midterm, thinking about the curve and sketching out all the small rectangles inside, that takes too much time. We should just be able to do the algebra without the need of drawing a diagram. So let's say the area approximates to. Area approximates to. Well, we know that the length of each rectangle is 1, or the width, and we have 4 rectangles, all the same interval, so we can just keep that 1 on the outside here. So we're going to use the shortcutted approach. So let's just say delta x was, say, 2, then we would put a 2 here. If delta x was, say, 0.5, we'd put a 0.5 here, so on and so forth. On the inside, we are considering the MRAM, so the middle of each interval. So the first interval is a length of 1, and it's going to go from -5 to -4. What is perfectly in between -5 and -4? -4.5. So we're going to find f of -4.5. That's our first rectangle. And we have to continue this pattern, so we're moving 1 to the right. What's perfectly in between -4 and -3? Well, that's -3.5. So I'm probably going to need to extend this out a bit. So on and so forth. So you'll note that the pattern is going to, the x value is always going to follow the delta x here. So this difference is 1, the next difference will be 1, and so on and so forth. So it's going to be f of 2.5, and we have 4 rectangles, so I have 1, 2, 3 so far. This will be f of -1.5. Okay, and then close that parenthesis there. Okay, so we'll say, well, all right, this expression is equal to 1 times, plug in a -4.5, so it'll be -5 over -4.5 plus -5 over -3.5 plus -5 over -2.5 plus -5 over -1.5. So you would evaluate this at this point. Obviously, it's not very simple to calculate 5 over 3.5. So we'll just say that this expression is equal to, it's 496 over 63. Okay, so our area approximates to this expression. It's about 7.83, 7.873. So yeah, this is all good and fun until it gets to a point where you need a calculator, in which case you would just use the calculator to find the actual area. But procedure here is still all the same. With MRAM, you want to go in between each value. So I guess now I can do the drawing just to kind of convince you further, and I'll do it over here. So -5 over x looks generally like this. But if I drew this absolutely perfectly, it would be right smack dab through the middle. The curve is cutting through the middle of each width. All right, for the next one we have this quadratic. It's a parabola from 0 to 4, and we have 4 rectangles, 4 trapezoids. Here we're doing a little bit of RRAM. It's the last of the 3 rectangular approximation methods. Okay, again, we're pretty lucky with the interval. Don't want that to be too much strain in terms of the process. We can just say, well, all right, delta x is equal to positive 4 minus 0 over the number of rectangles or trapezoids, which is 4. So again, we're getting delta x of 1. All right, so these are pretty nicely spaced out rectangles and trapezoids. Let's do the rectangle approach first. So the area will approximate to. Area will, trying to do the squiggle. There we go. All right, we have the 1, so my delta x, and these are, again, equal lengthed subintervals. So these cases are a little bit prettier to play around with. We can use this shortcutted approach. All right, we are doing right endpoints. So we're starting on the far right this time around. The first rectangle goes from 0 to 1. What is the rightmost value from 0 to 1? It's actually 1. We're starting on the far right end on this for this story here. So we're going to do f of 1. Now we're going from 1 to 2, and the interval from 1 to 2, the rightmost number is 2. And then we continue that pattern. Okay, so we're just plugging in these values now. So after throwing 1, 2, 3, 4 in and adding all those values, I just did that in a calculator. I ended up getting exactly 15. That's a nice, pretty number. All right, let's do trapezoid approximation for this. This is the new element to what we're doing right now. We have to find the area of each trapezoid, so perhaps now a drawing would be beneficial, since we're kind of doing this one for the first time. The way that this is going to end up looking, it looks a little like this. And I have a very small slither of empty space in between the blue trapezoid and my curve that is going to pretty much tell us that this is going to be an underestimation. This is not going to be perfect, obviously. It's going to either be an over or underestimation. It's a small underestimation because I have all these little curved spaces that I am missing out. So anyways, let's actually finally play around with the area of each of these trapezoids now. We know that the area of a trapezoid is 1/2 b sub 1 plus b sub 2 times h. The length of each and every trapezoid here, if we view these trapezoids on their sides, this length of this trapezoid is 1, this one's 1, this one's 1, this one's 1. The intervals, this delta x, is actually straight up the height of each trapezoid. It's just they're on their sides, all the trapezoids. So what we need to find is b sub 1 and b sub 2 in all of these cases here. So when I approximate this area, I'm going to say the area is approximately equal to, what's going to be on the outside is our h and our 1/2. In this case, our h is 1, so I'm going to have a half sitting on the outside here. And I still want to use this shortcutted approach. I just have to find the sum of each b sub 1 and b sub 2. So actually what's going to go on here is I'm going to have this kind of idea going on. I'm going to have 4 mini sums inside of here. So b sub 1 and b sub 2 for the first trapezoid is going to be f of 0 and f of 1. So I can plug those in. 0 plus f of 1. This length right here is b sub 1, and that was f of 0. This length right here is b sub 2, which was f of 1. Now, the bottom piece, this f of 1, used to be b sub 1. It's now the b sub, or it used to be the b sub 2. Now it's going to be the b sub 1 of our next trapezoid. So it's going to go from f of 1, that's the height of the next, this is the upper base of the next trapezoid, and my b sub 2 is going to be f of 2 this time around. I can continue this pattern, looking at the next trapezoid. My b sub 1 is now f of 2, so it is now your turn to be the b sub 1. And then the b sub 2 here is going to be f of 3. And then one more time, my b sub 1 is now f of 3, and my b sub 2 is f of 4. So f of 3 plus f of 4. Yeah, kind of had to cram that in there. But you'll sometimes see in textbooks the trapezoid method is, it has its own shortcut formula. And I guess I'll write it in its representation right now, because you'll see that f of 1 repeats twice, f of 2 repeats twice, f of 3 repeats twice. Any middle value is repeated, where on the ends, f of 0 and f of 4, you only see it once. So you might see a formula shortcutted that way in a textbook. I don't really teach it that way, but you could see it in this possible light. You could see it as 1/2 times f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3 and then a single f of 4 at the end. You could see it this way, is all I'm really just saying with that. Anyway, throw all this stuff in. So plug in your f of 0, that comes out to 5. F of 1, I don't know what that is, it's 5.5 or something like that. Throw in all these values, do some algebra 1, and you should end up getting 17. I think this comes out to 34 on the inside here, and half of 34 is 17. So we stated earlier that this is an underestimation. So 17 is really close to the answer, but not quite it. It's worth noting that RRAM is also an underestimation. Note that at first we're counting too much area, but then this kind of overpowers it, this missing area on the right two rectangles. So with that said, you do kind of get to this point where this area gets larger than this additional area we accidentally added on at the start. So anyway, 17 is getting closer to our actual answer, point being. 15 was a little far off, 17 is getting there. Let's actually calculate this for fun. I'll just throw it into a calculator. What is the actual area? Well, let's just kind of do the calculus on that. We would integrate this from 0 to 4. So we would integrate negative x squared over 2 plus x plus 5 dx. I'm going to throw this into a calculator to see what the actual area is. So after throwing it into a calculator, and of course we could just do this ourselves, but I'm assuming some people are watching this without knowing how to actually find the area by hand. This does come out to 17.3 repeating, so trapezoid was pretty close. These little slivers were largely negligible. Right, take this as a ratio 17 over 17.3 repeating. That's like 90-something%. That's very close. So 98%. It's almost there. Trapezoids make great approximations. All right, last one we're looking at is a little different. I don't know the function. This is a fancy way of saying, hey, find the area under the curve of our function from 0 to 10. And we're only given this snapshot image of it. We're given just these little moments that, okay, well at 0 we're 7, and at 1 we're 5, and then we're given a moment at 2, 8, and 10. All we can do here is approximate. So sometimes it's tempting to say going over approximation isn't that handy, isn't that useful, because you can actually just find the area by hand via integration. Or you can just throw it into a calculator and it does the integration for you. But what if you don't have all the information at your disposal? You don't know the function, in which case you're forced into an approximation method. So what I want to do is I want to do an LRAM and an RRAM with just this data set, and you'll note these are uneven interval lengths, so we can't use that nice shortcutted approach where we have the width of each rectangle on the outside on the left and all the heights on the inside, or lengths on the inside. We unfortunately have to find each independent area. So with LRAM, we want to start on the very far left point. So we want to start with this value. We want to start with 0, 7. So we'll say the area approximates to. Okay, so the first width of the rectangle, and actually I can even, I guess, draw this out. For LRAM, first rectangle, I want it to be including the left point, and we're assuming this is continuous, by the way, so we just don't know how this pathing works. Perhaps it is just as nice as this. Who knows? It could also have a lot of twists and turns to it. This is just an approximation and I don't know the full snapshot, so a lot of this is kind of just guessing in the dark. It's going to look like this because I know that at 0 I go up to a height of 7, and I know that I stop at 1 because I want to start my next rectangle there. So that would be my first rectangle. My next rectangle would go like this. My next rectangle will go up to the next point that I know, which is 2, 4. But here's the thing, I don't know anything that happens from 2 to 8. I can't continue with this nice interval length of 1. I don't know anything going on in between here. I'm forced into making the width of this next rectangle pretty large. So that's why we can't really use the same width every time, because very clearly this is not the same width as these two. Next rectangle I can create is from 8 to 10, so would look like that, and that would actually conclude the 4 rectangles I'm finding here. So I have 1, 2, 3, 4 intervals I could play around with, so 4 rectangles that I can create. And this is just for LRAM, and maybe in red I'll do RRAM. Okay, so first rectangle has a width of 1 and a height of 7, so it'll be, we'll just do it this way, 1 times 7. Next rectangle, still a width of 1 and a length of, this time, 5, so it'll be 1 times 5. Okay, whoa, look at this width. What is that going to be? So from 2 to 8, 1, 2, 3, 4, 5, 6. And that height is going to be at 4. We're going to take the left endpoint, so it's what occurs at this input of 2. It'll be 4. Very lastly, looks like we have a width here of 2. And what's that height? What is that? F of 8 should be 3. So you'll note we didn't touch this 5 at all. Maybe we will with RRAM. So anyway, what does this end up coming out to? Should be 42. 7, 5, that's 12, 24, and 6, that's 30. 12 plus 30 is 42. Okay, so this is the area approximation taking the left endpoints, but in red, let's consider the right endpoints. See what happens there. So with the right endpoints, I want to end on this value actually. So this first rectangle is going to be below it. Okay, we're going to continue the pattern here. I want my next right endpoint to be on, well, instead of 5, now 4. Okay, here I'm going to consider my next right endpoint. So my right endpoint was once 4, now it's going to be 3. So you'll note that this rectangle is now underneath this fictitious curve that I drew. It's going to be a lot smaller of an area because we don't have this slither here, so we're on 1, 2, 3. And then very finally here, we're going to take this last endpoint. So it does make up for it, some of the losses here. These first 3 rectangles were all immediately underneath it, but at the end here, it's actually made up for it because we have a 10, 5 value, and in which case we go up to this right endpoint. So you'll note that all right endpoints are touching the curve, whereas in the last one, all the left endpoints were touching it. Oh, I'm not done yet. I should find the area, huh? So the actual area, this one I don't have. So we'll do this one mentally here. All right, so first interval length to consider, it looks like it's 1. And this time around we're taking the height of 5, not the height of 7. Plus another interval length of 1, and I go all the way up to 4. This interval length we established earlier was 6, but now instead of going up to 4, we're going up to 3 because we took the right value, not the left. So it'll be 6 times 3. And then one more thing, we're finally using that 5 now here. This final rectangle, it's got a width of 2 and a height of 5, so it'll be 2 times 5. That's a 2 times 5 at the end there. So you'll note that in the left rectangular approximation method, we used the first 4 values here, 7, 5, 4, 3, 7, 5, 4, 3. Whereas in the right rectangular approximation method, we took the last 4 of the 5. 5, 4, 3, 5, 5, 4, 3, 5. All right, whatever this comes out to, 5 plus 4 is 9, plus 18 is, well, that's 27, plus another 10. Is that 37? I sure hope it is, because that ends the video. Please continue to math on, and I will do the same. See you the next time.